Hello viewers, I am Kausalya. Today we are going to solve problem number 4 and the problem is obtain the state space representation for the electrical network shown below. So this is our given problem, right? And here we are having an input voltage and we are having two resistors, right? One inductor and two capacitors, and here in the problem they had already mentioned, and this is V1 and this node stands for V2, right? Now we will proceed with the answer. So here the first step is we are going to find the currents which flows in different branches of the given circuit. So here in this case, initially we are assuming the current flowing through this part is I1, right? So at this node, this I1 gets divided into two. So one part is I, and what about the current flowing through this path? It will be I1 minus I, right? For example, just for example, right? So here consider some 5 amps of current flowing through this part, and here we are having 3 amps current flowing away, right? So here comes 5 and here goes 3. So 5 minus 3 remaining is 2, and that 2 amps will be flowing through this path, right? Then again this current I1 gets divided at this node V2. So here the current flowing through this line will be I minus I2. Therefore the current flowing, first here we are assuming the current flowing through this path as I2, right? So the current flowing through this branch will be I minus I2, right? Again the same thing, the current gets divided at nodes, that's it, right? And here we are going to apply Kirchhoff's voltage law since we are having loops, okay, many loops. So here I am assuming this loop as 1 and this loop as 2 and this as 3, right? So now we are going to apply KVL to all these loops. So again here you see the current flowing through this path, right? So I1 R1, whenever the current flows through resistor, it creates a voltage drop, right? So here it is minus I1 R1. And again you see the direction of current flowing through this capacitor when considering loop 1, it flows from plus to minus, right? So here voltage across this capacitor is V1, it is directly given, right? So here it is minus V1. And again when you consider the supply voltage source, here it will be minus and here it will be plus, right? The current flows from minus to plus. Therefore here we are putting plus E equal to 0, right? So we had applied KVL to this loop 1 and it is done here, right? So here I1 R1, that is voltage drop across this resistor R1 will be I1 R1. Okay, since it is a voltage drop, here and minus is included, right? And again when you look at this part, current flows downwards, that is from plus to minus. Therefore the voltage drop across this capacitor is again minus V1. And when you consider this supply voltage, here the current flows from minus to plus, therefore it is plus E, okay, which is equal to 0, right? And now we are going to apply KVL to the loop 2. So when you look at this loop 2, again the same thing. So the voltage drop across this inductor is given as L1, that is minus L1 into di by dt, because the current flowing through this inductor is I, right? So L1 into di by dt. And again when you look at the current flowing through this capacitor, it flows from plus to minus, right? So here the voltage drop is minus V2. And again when you move over here, the current flows from minus to plus, therefore this voltage is plus V1, right? So this forms our equation number 2. Again when you consider loop 3 here, the same thing. Here the current flowing is I minus I2. So therefore voltage drop across this resistor is I minus I2 into R2. Since it is a drop, here we are including minus, right? And again here the current flows from minus to plus, therefore this voltage drop is plus V2, right? So this forms our equation number 3. Then here we are going to frame our state variables. So here the state variables are x1 is equal to v1, right, and x1 is equal to v1, that is v1 and v2 are mentioned, right? So these are all, it is must to include these two as state variables. So v1, x1 is equal to v1, and here x3 is equal to vt. What about x1? The current I which flows through this part is taken as x2, because these are all the things which are given in the problem, right? We are not assuming by ourselves. So v1, I and v2 forms the state variables, right? So am I making the things clear? And finally, as we all know, the input voltage E is always represented as U here, right? Then we are proceeding with the current flowing through the capacitors. So here initially I am considering this C1, right? So current flowing through this capacitor is given by, what is the expression? The actual current flowing is I1 minus I, right? The expression for current flowing through the capacitor is C1 into dV1 by dt, right? This is the current flowing through the capacitor from the diagram, and this is the formula of current flowing through the capacitor. Both should be the same, right? So here, and again we are rearranging. So finally we are getting an expression for dV1 by dt. Okay, this is our equation number 4. Again we are considering equation number 1. Right, this is our equation number 1. Here we are rearranging and finding the value of I1, right? So it is quite easy, right? I am moving this part to the, I am moving this part to the right hand side. So this minus I1 R1 becomes plus I1 R1. And here minus V1 plus E is rewritten as E minus V1. You see, plus E minus V1, right? And here we are calculating I1. The next step is we are going to calculate this I1 again in the equation number 4. So this is our equation number 4, and I1 is replaced with this expression, right? And now we are going to replace it with the state variables. So here V1 is nothing but, E is nothing but U, and V1 is nothing but x1, and here this I is x2, and again dV1 by dt can be represented as x1 dot, right? So here again we are simplifying the expression. So U by C1 R1 minus x1 by C1 R1 and minus x2 by C, which is equal to x1 dot, right? So name this expression as expression number A, because we had framed an expression for x1 dot, right? And the next one is, now we are going to consider the current which flows through the another capacitor. So again when you look back at the diagram, now when you look back at our circuit, the current flowing through this capacitor C2 is I2, right? So again the voltage across this capacitor C2 is V2. So here I2 is nothing but C2 into dV2 by dt, right? So again when you rearrange, we are having an expression like this. Let this be our equation number 5, right? So again from equation 3, so this is your equation number 3. We are simplifying, that is initially we are going to multiply this R2. So I R2, I2 R2 plus V2 is equal to 0, and again find an expression for I2, right? After finding the expression here, just substitute this value again over here. We have to substitute here, right? So I2 is given as I minus V2 by R2. So when you substitute it over here, again we can replace these elements with the respective state variables, yes or not? Here we are having I and here we are having V2. So just replace with the respective state variables, I with x2 and V2 with x3, right? So again dV2 by dt can be expressed as, V2 is nothing but x3. Once it get differentiated, it is represented as x3 dot, right? Then mark this expression as B, right? Again now we are considering our equation number 2. So this is our equation number 2, right? Again we are rearranging this equation. So when you rearrange, finally di by dt is given by this expression, right? This is very simple, no need to explain, I hope so. So after simplifying, just replace with the state variables. One is with x1 and another with x3, right? v1 as x1 and v2 as x3. So again di by dt is nothing but our I is nothing but our x2. So di by dt is x2 dot. And finally we are having an expression for x2 dot also. Okay, mark it as C. So now we are going to write all these three expressions together, right? So A, and this is your B, and this is your C, right? This is your C and this is your B here, right? So after writing these expressions, finally we are going to represent it in the form of a matrix. So when you represent it like in the form of matrix, again the same thing, x1 dot, x2 dot and x3 dot, right? And here the first parameter which should be included in the column matrix are x1, x2, x3. So write it. Here the coefficient of x1 in the first expression is, it is minus 1 by r1 c1. So it is written here. x2 is minus 1 by c. There is no x3. So it is 0. Right. Again when you look at your second expression, that is b. This is our x2 dot, right? Okay, we have to write by x1 dot, x2 dot and x3 dot, right? So when you look at our x2 dot, here again the coefficient of x1 is 1 by L1, right? So 1 by L1, and here the coefficient of x2 is 0, here it is plus, right? And here the coefficient of x3 is minus 1 by L1. And again x3 dot, again we are having x2 and x3, therefore the coefficient of x1 is 0 and coefficient of x2 is 1 by c2 and this x3 is minus 1 by r2 c2, right? Plus again here in the first expression we are having a term u along with some constant, right? So again as we all know, u is nothing but our input matrix, so u, and here the coefficient of u is 1 by r1 c1. So 1 by r1 c1. In the second and third expression we don't have u, so here we are mentioning it as 0, and finally this is our answer, right? So the key thing to be noted here is, the first step is you must analyze the currents which flows in different parts of the branch. That is your first step. And the second step is you have to frame expressions using KVL, right? So that is the second step. The third step is you have to calculate the current which flows through the capacitors, right? C1 and C2. Then you have to wisely replace the values with the previously formed loop expressions, right? So when you substitute, rearrange, and when you replace the term with state variables, finally we will be getting this matrix, right? So here comes the end of the problem. If you have any doubt, let me know in the comment section. Thank you.